So we find a limit by plugging numbers in for a being with the limit is approaching. There is a shortcut, and the shortcut we're going to be using all throughout. So this shortcut is the rule of thumb. If f happened to be a rational function, a polynomial function, a radical function, or a trig function, of course further defined, then if taking the limit as x approaches a value of one of these functions, you simply substitute the value in. If you get a number, you're done. That's the limit. If you get a number over 0, you're going to say it does not exist. The answer is actually either positive infinity or negative infinity. We'll focus on that later on. But you could simply say it does not exist. But if you get 0 over 0, which is the majority of the time, then you're going to have to simplify. And we're going to do some examples to match everything you come across. Evaluate the limit if it exists. Again, we're not going to make a table and choose x and x squared plus x over. We're not going to do that anymore. Evaluate the limit, and something like in the lines of without a calculator. There. So in this case, we substitute -1 in and we see what happens. If we substitute -1 squared is 1 minus 1, that's 0 over, and this will be 1 minus 3 plus 2, which is 0. If it's rational, it's simple. That's how my limits look like. When you write limits as long as I've been writing them, that's how they look. So what you do, you try to cancel out the 0 over 0, meaning you factor in this case, and the denominator will be x plus 2 over x plus 1. And you notice those cancel out. Keep in mind, what you just canceled out is really what's causing the 0 over 0. And once you cancel something out, you restart this shortcut. You substitute the value in, you get -1 over 1 minus 2 is 1, and that's your limit. If you were to plug in numbers above -1 and below -1, you would have gotten the same thing. Same deal here, you substitute x equal -1, you get -1 plus 2, that's not a 0, over 1 minus 3, you get 1 over -2, so it's -1/2. Again, if you were to substitute numbers above and below -1, you would have gotten a -0.5. Here you substitute 0 for h, you get 1 squared minus 1, that's 0 over 0, so we're going to use manipulation. What can you do here? Well, you could FOIL this. That's 1 plus 2h plus h squared minus 1. The ones cancel out. Limit as h approaches 0 of 2h plus h squared over h. You could see that h is common in both of those terms. You could factor that out. And once you cancel out, again, notice that's what was causing the 0. That's the limit as h approaches 0 of 2 plus h, and if you replace h by 0, that will simply be 2. Radicals are slightly different. If you throw a 3 in there, 3 plus 1 is 4 squared, of course 2 minus 2, that's 0 over 0. With radicals, there's one way of proceeding. That makes it easy because you know exactly what to do. What you do, you multiply by the conjugate of the radical. I know you're used to rationalizing the denominator, but in this case, we're not trying to simplify, we're trying to find what the limit is. You multiply by the conjugate, the same exact radical, make sure that those are opposites. And we know if you multiply conjugates, you get the first squared. If you square y plus 1 radical, you get y plus 1 minus. If you square that 2, you get a 4. The denominator, you leave as you see it, a bit messy, but it's okay. And if you simplify the top, you'll notice that's y minus 3 over y minus 3 into square root of y plus 1 plus 2. And you notice that those cancel out. And in that case, you're left with the limit as y approaches 3 of 1 over the square root of y plus 2, y plus 1 plus 2. And if you replace y by a 3, 3 plus 1 is 4, square root of 4 is 2 plus 2. That limit will be 1/4. And notice I'll keep on writing a limit until I substitute the value in. You should do the same. And if I look at the next problem, negative 2 squared, that's 4 plus 5, that's 9. Square root of 9 is 3 minus 3 is 0. Negative 2 plus 2 is 0, so we're going to do the same thing. Actually, if you move this a bit to the right, and you multiply right there by the conjugate. So the conjugate will be the same radical that you see. Top and bottom, a ratio of 1, and the opposite of that sign. So again, multiplying conjugates gives you the first squared. If you square a square root, it cancels out. That's the purpose. Minus 3 squared is a 9 over x plus 2 times the square root of x squared plus 5 plus 3. So the top will be x squared, 5 minus 9 is 4. And at any given stage, if I replace x by negative 2, I'll still get 0 over 0 because I didn't cancel anything out. Now I could factor the top. And I notice that this cancels out. Once you cancel something out, you're going to restart the shortcut. That is, you substitute x equal negative 2 again and see what you get. If you replace it x by negative 2, that's negative 2 plus 2, which is 0. And negative 2 in there will give me a 4. 4 plus 5 is 9. Square root of 9 is 3 plus 3. So I get 0 over 6. 0 over 0 is undefined, but 0 over any non-zero number is 0. We have two more types of problems that we come across. Here, complex fractions. If you let h equals 0, you get 1/2 minus 1/2, which is 0, over 0. So limit as h approaches 0. This is really 1 over 2 plus h minus 1 over 2 over h. You're going to have to clear the complex fraction. The way to do that, the quickest way, is to find the LCD for the top and the bottom combined. That's 2 into 2 plus h. So this is missing a 2. Multiply top and bottom by 2. This is missing a 2 plus h. Multiply top and bottom by that. And this is missing all of it. And once all the fractions have the same denominator, you ignore it. That becomes a single fraction. So if I read the top, 2 times 1 is 2, minus parentheses 2 plus h, and the denominator is all of this mess. And if I clear the parentheses, I notice those cancel out. I'm left with the limit as h approaches 0 of negative h over 2h into 2 plus h, and you notice those cancel out. And once I cancel out a quantity from the top and the bottom, I restart the shortcut, replace h by 0, and the answer is negative 1 over 4. So it takes that much work. Same deal with this complex fraction. Here, if I replace h by 0, 1 over x minus 1 over x is 0 over 0. Again, what I'll do, I'll simplify this complex fraction and make it into a single fraction. And you do that by finding the LCD for the top and the bottom combined. The LCD is x times x plus h. So the first fraction is missing an x, the second is missing an x plus h, and the third is missing x into x plus h. And again, you ignore the denominators if they're all the same, because if you multiply by the reciprocal, they cancel out. That's the limit as h approaches 0. And here at the top, x times 1 is x minus 1 times x plus h, and the denominator is hx into x plus h. So this is the limit as h approaches 0, x minus h over hx into x plus h. That's the limit as h approaches 0. The x's cancel out. Do you notice that those cancel out now? And once I cancel a factor out, I reset the limit, meaning the shortcut again, replace h by 0. And that would be negative 1 over x squared. And that would be it. There's still one portion of this section I'm going to leave for next time, along with section 2.3. And we'll conclude this next time.